Hello everyone, my name is Zhang Boshen from Shanghai Jiaotong University, and the paper's title is Distributed Hierarchical Control for VSC-Based DC Microgrids with AC-DC Coupled Strategy, and the paper ID is 79. The presentation consists of 5 parts. First, the introduction part. Next, the hierarchical control with AC-DC coupled strategy. In this part, I will show the detailed control strategy. Third, the system modeling part. I will show the model process. And fourth, the simulation studies. And at last, the conclusion. First, the introduction part. As we know, the hierarchical control strategy can achieve voltage regulation and current sharing. However, traditional methods usually use DC voltage or DC current loop to regulate the DC voltage and current, and the bandwidth of the DC control loop will limit the dynamic response of the system. In the proposed control, the DC voltage and current control loops are eliminated, and a faster dynamic response can be expected from the proposed control strategy. As we can see, the secondary control gives the reference of the data ID with a compensation term, and the primary layer gives the reference of the ID to the vector controlled VSC. The control objectives of the proposed hierarchical control is similar to the traditional methods. First is the voltage regulation. The average output voltage of the sources should be the nominal voltage. And second, the output current of each converter should be proportional to its own power rating, which is denoted as IC here. In this slide, we show the detailed primary layer and secondary layer in the proposed hierarchical control. First, in the primary layer, we use an ID to V troop characteristic as shown in the figure above. And the D-axis reference of the AC current is generated from the troop characteristic, and a compensation term of ID is named delta ID from the secondary layer, and is generated as a sum of two PI controllers. The first PI controller is used for the voltage regulation, and the second PI controller is used for the accurate current sharing. And the current sharing is realized by an non-linear disturbance observer. At the same time, the average estimation of the voltage and currents are generated from a distributed algorithm. It is worth noting that the algorithm is not limited to one, and any algorithm can be used as long as it can provide the precise estimation of the average value. In this part, the detailed control block diagram is shown here. First, for the secondary layer, the AC-DC coupled secondary control uses two PI controllers to generate one compensation term for the primary layer. And in the primary layer, a droop characteristic with droop gain K is used to generate the D-axis current reference directly. And for the inner loop, the vector control is used for the VSC control, and to control the active power, ID is used, and the IQ is set controlled to 0. And in this way, the system can work according to the ID to V droop characteristic with a compensation term directly sent to the D-axis current. In this part, we will show the system modeling. The model process of the whole system is from part to part and then combined together. First, the VSC part is a traditional physical representation of the voltage source converter in DQ frame, and the primary layer uses the proposed ID to V droop characteristic, and the secondary layer uses two PI controllers to compensate for the voltage and the current sharing ratio. And the final state vector is composed of the proposed state variables, and Z is used in the nonlinear disturbance observer. It can be seen from the modeling verification that our mathematical model is perfectly consistent with the simulation model in MATLAB, which shows the mathematical model is correct. Based on the established state space model, the stability is analyzed in this page. As we can see, when the droop gain is becoming smaller and smaller, the eigenvalue of the system is moving towards the right half plane, and when the droop gain is smaller than 0.06, the system is becoming unstable because there are right half plane poles or eigenvalues of the system. So when we design a system with the AC-DC coupled droop characteristic and the hierarchical control, we cannot set the droop gain too small in our system. It can be seen from the simulation results that the dynamic response of the proposed method is faster than the traditional method, and it is worth noting that there is no overshoot when the load increases. The undershoot is also much smaller than the traditional method. Okay, finally, we make a conclusion. An AC-DC coupled distributed hierarchical control strategy is proposed for the VSC-based DCMG, and the whole system model of the control strategy with the MG system is established, and after checking the performance of the proposed control, we can see faster dynamic response is shown when compared with the traditional method.